talks there. Yeah. Okay, so some of you might have noticed the price of energy has been rising lately. Oil, natural gas, even rumors the price of gasoline's gone up. Our next session here is, can space help solve Earth's energy crisis? Our moderator will be Mark Jannot, who is the editor-in-chief of Popular Science magazine. And Mark. There you go.
Hi, everybody. As Bob just said, the subject of this panel is, can space help solve America's energy crisis, or Earth's energy crisis? And I'm sure that anyone who has popped in on any of the space elevator, or in particular solar power satellites workshops, has a strong sense that for the two guys who are either up on stage right now with me or about to be as soon as John gets his PowerPoint loaded up there in the back, for these two guys, that is something of a rhetorical question. But we're not going to assume that you've got a deep grounding in either space solar satellites or in the space elevator to sit in on this. And I, for one, am not going to proceed as if it's a foregone conclusion that the answer to that supposedly rhetorical question is, yes, you idiot, of course space can help solve Earth's energy crisis. We're going to see whether these guys can convince us. I'll introduce them in a second and give them a chance to give them their case, but I first want to give you a sense for where I'm coming from as your moderator. I'm the editor of Popular Science magazine. And when George Whitesides asked me to moderate this panel, he had no idea the extraordinary coincidence of that, because on Monday, 2 days from now, my staff will be shipping our July issue with a cover story called The Future of Energy, 10 Technologies to End Our Oil Addiction. And even more uncannily, here is a rough mock-up of one of the covers that we've been considering for the issue. Now, I think John would probably say that that is a tolerably accurate artist's conception of a solar power satellite, or at least I hope he would. We had a very good reason to suppose that if we put that image on the cover, the magazine would sell very well on newsstands. For one thing, our readers love space-oriented covers. And for another, it had been proved just a year ago that our newsstand buyers would snatch up an issue-oriented cover depicting far-out, space-based, high-tech solutions. And if you throw up the next image, this cover last August, which is coming up, is about spectacular technologies to halt global warming. And that's not it. Huh? Yeah, I know, exactly. Halted in its tracks. Okay, here it is. That's a sort of rough version of that cover. The logo is kind of screwed up. But and it depicts one version of the space screens or mirrors that Greg Benford mentioned at this morning's sci-fi panel. Pretty far out. And it shocked everyone in my circulation department by selling 135,000 copies on newsstand, which was our third best-selling cover last year. So I was motivated to consider the solar power satellites for our cover, but I didn't choose that cover, the one that I just showed you. Maybe you can throw it up again. And the reason why I didn't choose to throw the solar power satellites on the cover is, I think, relevant to our discussion today. I didn't choose it because I think it's just too out there for my purposes. We at Popular Science have a proud history of giving our readers holy shit glimpses at far out futures. But this cover package that we're closing on Monday is about our 10-step plan to wean America off of oil. And it's crucial, I think, to communicate to readers and newsstand buyers that the plan is doable and relevant today. So I rejected the cover because I didn't want people glancing at it and saying, Jesus Christ, that thing is at least 50 years off. What does that have to do with the $4 I'm paying at the pump? Or how in the hell is that going to save us in time from cooking ourselves with global warming? And so my challenge to you guys, I guess, if you choose to accept it, is to convince me that I made the wrong choice and that I should have gone with the solar power satellite cover, that solar power satellites aren't so far out as to be irrelevant to our conversation about fossil fuel dependence, global warming, etc. And with that, I'm going to give these guys each a chance to give us a quick backgrounder on their area of expertise. I hope reasonably quick so we can have some questions, both from me and from the audience. And I'm going to start with John Mankins, who was the manager of Exploration Systems Research and Technology within the Exploration Systems Mission Directorate for NASA for 10 years. He was the manager of Advanced Concept Studies at NASA, leading studies of space solar power, highly reusable space transportation, affordable human exploration, and other topics. He was the creator or co-creator of the MagLifter electromagnetic launch assist system, the internet-based NASA Virtual Research Center, the Solar Clipper interplanetary transport vehicle, the Sun Tower space solar power system, the hybrid propellant module for in-space refueling, the HAVBOT mobile planetary outpost architecture, the advanced technology life cycle analysis system, and others. Mankins has received numerous awards and honors, including the prestigious NASA Exceptional Technology Achievement Medal, for which he was the first recipient, and now he's the president of Artemis Innovation Management Solutions, a management consulting research and development startup serving clients from government, industry, and not-for-profit sectors, and I believe one of the greatest advocates for solar power satellites in space, which he will just tell us about right now.
Good afternoon. I appreciate the previous session being just a few moments late in finishing, since I was a few moments late in finishing, and so we were very well synchronized. What I'd like to do is run through about 142 charts with you. If you've seen me give this briefing, then you know that'll take about 12 minutes. No, it'll be about 12 minutes, but it's not 142 charts. Next, please. There we go. So it's about 20% of the charts are going to have to do with, got it. Thank you. With background about 40%, or about 40% of the time on, and a quarter of the charts on the trade space and some key issues, and a little bit on new concepts and some of the challenges we face in realizing space solar power systems of all types. I don't know if very many of you have looked at the original patent that was filed by Peter Glaser, who invented the solar power satellite in the late 1960s. The patent was issued in the early 1970s. If you have not, then I do certainly recommend it to you. It is fascinating. Of course, Peter Glaser, then VP at Arthur D. Little, invented the idea of the solar power satellite in the context of significant advances in photovoltaics that had been realized because of the space program, and because of the work of this man, Bill Brown, who is now no longer with us, who invented some of the critical technologies having to do with directed wireless power transmission. Of course, Nikola Tesla was quite interested in the idea of wireless power transmission. That's that central photo of a man in black. That's Tesla sitting in the midst of this tremendous arcing generator of high voltage DC. The only dilemma with his plan for wireless power transmission, which is 100 years ago, was that when challenged by Wall Street, I believe, according to the story, it was J.P. Morgan, how are you going to, this is fantastic, this is incredible technology, how are you going to bill for it? What do you mean bill? This is a service, we're just going to provide it. Because at the time, you could put a lot of electromagnetic energy into the air and you could take it back out through coils, but you couldn't bill for it. And at which point his funding stopped. However, Bill Brown, developing the idea of directed, focused wireless power transmission using phased array technologies, enabled a whole range of studies, first in industry and then through a Department of Energy, then it was the Energy Research and Development Agency, and NASA studies in the late 1970s, which resulted in the reference system concept there in the lower left. Unfortunately, at the time, and this is in the context of a tremendous series of oil shakeups and a very friendly administration, that of Jimmy Carter, the proposed plan was to proceed rather aggressively with the development of these very, very large-scale systems, and when it reached the Office of Technology Assessment and the National Research Council, the evaluations of the proposed plan were fairly negative. And the oil prices dropped. There was a new administration with new priorities, and the whole thing was shelved. During the 80s, U.S. activities largely ceased. There were a series of ongoing international activities, which we can talk about at another time. But in about 10 years ago, significant activities, modest activities, got started again within NASA in the context of Mr. Golden's, then Administrator Golden's, interest in advanced concepts and highly stimulating future pathways. He created an Advanced Concepts Office within the then Office of Space Access and Technology, in which I was located, and from which the so-called Fresh Look study was implemented. This study resulted in about 3 years in a series of new concepts using new technologies, which we believe validated that space solar power systems, beginning in the relatively near term in the 100 kilowatt to megawatt class, were in fact technically feasible, and that from those you could stepwise progress to systems in the many megawatts to gigawatt class. We presented this in the form of a series of roadmaps and systems analysis modeling results to the National Research Council just about 20 years late after their initial very negative review of the preliminary plans for solar power satellite systems, and received actually a very positive response. Not to the marketability of SPS, because they decided they were in no position to judge the economics of future energy needs, but rather in terms of the technical plan, i.e., was it a technical roadmap that was credible and that could in fact be achieved for the kind of budget numbers that we were talking about? And the answer to those questions were yes, plus a whole bunch of recommendations on how we could do things better. So what about that? So that's background. That's what's happened over the last 40 years plus. So what about SSPS? Why should you care? Well, if you look at the global energy marketplace, as we well know today, there is a tremendous surge in international demand for energy in order to promote the growth in per capita incomes among the populations of the developing world. For many, many years, in fact, going back into the ancient past, the distant past, the principal sources of energy for domestic use were things like wood and animal waste. These are actual photographs taken in India. More recently, industrial waste. This is a lady in the far right making briquettes out of the debris coming down, the ash coming down out of a coke plant. But assuming that not everyone would like to spend countless hours each day in the struggle to find enough energy to cook their meals and the struggle to find fresh water in which to cook them, and that there's a reason for future people to, in the future, for all peoples to enjoy a standard of living much greater than desperate poverty, then the kinds of curves you see in the upper right are going to happen. There's going to, with the fits and starts and economic issues, there's going to be tremendous demand for an increased energy globally. Looking out over time, the forecast in 1999 from the 20-year forecast, rather the 20-year forecast, looking back 20 years, looked like the curve up here in the upper right, with some variations depending on the economic growth. And during the last 6 or 8 years, those forecasts have not changed much. Here's a chart, 1980 to 2030, to compare with the 1970 to 2020, was in the Department of Energy's Energy Information Agency forecast this past February. Although I apologize that the curves are slightly different, but if you add the industrial, the residential, and the commercial uses of energy growth in annual electricity sales, what you get is a curve quite similar to the previous forecast, i.e. there's no uncertainty. It's well established and well agreed to that there's going to be this kind of very significant demand in energy. However, there's some question, and there's been a series of discussions about whether or not there's enough energy to meet the demand. And I put this up only for purposes of comparison. This is the Hubbard thesis. If you haven't Googled this, I certainly recommend it to you. There was a very nice article in Scientific American on this subject some years ago, and another very nice article similarly in the journal Science. This is by no means a shared perspective on what might happen in terms of global annual energy production. Normalized to oil. This is oil production. And in fact, if you compare the rather statistical and rather cautionary projection from the people who espouse Hubbard's thesis to the Energy Information Agency, what you see is the Energy Information Agency is that it's going to be up, up, and up forever with no particular decline of any kind. And so this is their reference forecast from this same January or February 2006 energy forecast of what's going to happen for oil imports during the coming years. I will mention that something I found enthralling in that report was a similar forecast for coal. Now, we all think of coal being the source that the U.S. is super abundant in. There is a chart which is far more dramatic than this one in terms of increases in coal imports over the next 20 years, which is fascinating. And I won't claim to understand all the reasons behind it, but in terms of the major sources of energy today, oil, natural gas, and coal, one of the areas which is forecast for the most dramatic increases in imports is coal. None of this, so far, takes into account another small issue, which is global warming. When we did the Fresh Look study in 1995 through 1997, this was a very problematic thing to even talk about. Similarly, by the way, you couldn't talk about the potential that proliferating nuclear reactor power systems around the world might lead to nuclear weapons control issues. That was something you simply couldn't talk about in 1995 to 1996. Similarly, there was a great deal of uncertainty, it continues to be a great deal of debate, but far less uncertainty about whether or not the emissions of greenhouse gases is leading to global warming. Very nice paper several years ago by Marty Hoffert and a team of co-authors basically made the argument that stabilizing CO2 is not a regulatory issue. Because of the vast demand and the vast need for new energy over the coming decades, there is no way that you are going to supply that energy, even with a mix of energy sources and the building of massive numbers of nuclear reactor power plants globally, that you're going to solve those issues without doing something about energy technology. And so there's this fundamental challenge. However, in thinking about space solar power systems as part of the solution, it is important to recognize that solar power satellites are a very complicated story. Nice thing in my paper, you can get it, I guess you can buy the CD. I'm not going to take the time to go through it. The physics of wireless power transmission is trivial. This is not fusion. This is not a challenge of the fundamental physics of how you achieve break-even power in a fusion reactor or what kind of fusion reactor you use. Physics is exceptionally well understood. However, it is a really complicated engineering problem with a whole host of interrelated issues having to do with the beam, the power transmission, how much the hardware costs that you put up into space, how you put it together, how you maintain it, the transportation system to get it in and around in space, into and in around in space, and so on. A couple of things are in here. I won't belabor them because of the time. I'll just mention when you go to higher frequencies, you can have the potential to get more power on a smaller spot in power beaming. However, based on existing devices, the efficiency with which you can move that power goes down and down and down. And so there is a tendency in trying to think about large-scale, industrial-scale space solar power systems, solar power satellites, to look to microwaves where the efficiencies are really quite remarkable, on the order of 80+%. Just a couple of quick notes concerning the reference system concept, which I mentioned before, and the fact that it did poorly in its evaluation. I'll mention that a couple of the reasons that it did poorly are in the lower left-hand corner. One, that everything had to be stick-built. And because it was stick-built, it required enormous investments in in-space infrastructure, tremendous in-space factories, thousands of robotics, thousands of robots, thousands or hundreds of astronauts in low Earth orbit and geostationary Earth orbit in order to put these stick-built monoliths together, each of which, looking at that central manufacturing plant, that's that cartoon there in the left, center left, the manufacturing plant is about the size of a Borg Death Star, the cube, the Borg cube. Each of those dwarfs a Borg cube. The Borg cube fits nicely into the end of one of those. Similarly, the launchers, this is 1978, the launchers were fully reusable, two-stage to orbit vehicles capable of launching 250 tons at a throw. The space shuttle, the current space shuttle, fits nicely on the wing of the lower one. And so these were stupendously large systems to launch big individual blocks which had to go up to these tremendously large factories. in the 1970s concepts. So even though there was no issue with the physics, there were tremendous issues with how you would actually deploy. In the 1990s, what we discovered is that technology had moved along, and that, like everything else, space solar power systems could benefit dramatically from Moore's law, i.e. it was possible to envision very, very large systems built out of many, many, many small intelligent systems. This is like conceptualizing your, I hold up my prop, my local cheater that allows me to be telepathic around the world, a cell phone, which is, I don't know, probably one of 20 or 30 or 50 of them that are in the room at the moment. Connected through a network, together it forms a global telecommunications system, which is truly awesome to envision, involves gigawatts of power, and is completely self-organizing and self-regulating within limits, although I occasionally drop offline, which I don't like. Because of this, we were able to envision completely different kinds of transportation systems, which were much smaller and much tractable, very, very different kinds of in-space systems which assembled themselves and relied on the advances in physics that had been made decades earlier. Still have a complex problem, and we've identified a series of crucial factors which will determine the economic viability of SSPS. The bottom line for the National Research Council review was that there's no fundamental technical problem with our current concept for SSPS. We do not depend on radically out of whack voltages or stupendous particular advances in propulsion or any of those things, but it will require some significant advances in how we solve these problems in order to get to economic viability. So things like your constraints on energy beam density, the thermal management, getting rid of waste heat in space is a big deal. When you've got an exceptionally large power system, it's a very big deal. How to install and manage and so on. Just for reference, you think, oh my God, solar power satellites, their rectennas, the receiving station is going to be unimaginably large. Just for reference, this is the Denver International Airport, a controlled airspace in western or eastern Colorado. And you'll see that a 1 kilometer diameter transmitter at 2.45 gigahertz, about 12 centimeters wavelength, gives you a very nice spot that fits tidily within the grounds of the Denver International Airport. If you went to 5.1 gigahertz, by reference, higher the frequency, smaller the wavelength, smaller the receiver for the same size of transmitter, you see that it becomes quite tractable, and it fits, in fact, rather tidily into one corner of the Denver International Airport. So even though these things are quite large systems, they're not larger or unimaginably large compared to things that we already build and take for granted. And what about similar systems? Well, here's the Arecibo, just for reference. It's about 300 meters in diameter, about 1/10 the diameter of what you'd have in mind. And just for reference, underneath the mesh, you can see at Arecibo, there's actually quite a bit of growth underneath. There's some question as to whether or not you kill the land, and the Arecibo mesh is quite comparable to what you'd need for a ground receiving station for a solar power satellite, using microwaves, not visible light. So what are the barriers? Certainly there's a whole legacy of issues with past concepts and systems, past programs. A lot of people got their careers burned by participating in the 1970s activities. All of them remember it. All of them don't want to repeat the experience. And so there's a very negative perception on those who participated in the first place. Second, competition for what is the vision. When I was at NASA, I tried hard to articulate the idea that advancing transformational new space capabilities, the things that let you do ambitious activities in space like solar power satellites, are good for everybody. They let you do more ambitious exploration. They let you do more ambitious science. The fact of the matter is, throughout all of the debates and all of the discussions within government circles in the past 10 years, there's been a fundamental competition, not for ideas, but for ideals. I.e., what kind of an organization are we and what are we trying to accomplish? That has been the fundamental barrier to getting something going in terms of technology development or a long-term plan for solar power satellites, even though they're tractable in terms of the physics, where other technologies like high-energy fusion are not yet validated at the physics level, but they receive hundreds of millions of dollars a year, decades before they will ever be operational. It's a fundamental problem. In terms of the technical challenges, there are a whole host of technical issues with the reference system. The very large crews, humans and robots I mentioned, very high voltage power management systems had to be resolved. We think we resolved that in our concepts of the past decade. Thermal management, the hardware costs, installation costs, all of these things lead into a very nice 90-minute talk about the technical solutions to these problems, which I will not now proceed into. I'll just mention 4 transformational concepts which in fact are all tenable today or within the next decade, which change the equation. They're game changers. One is intelligent modular systems, self-assembling networks, physically self-assembling and electronically and in terms of information, self-assembling systems made possible by Moore's Law. I've got a nice little cartoon up there of or a photograph of a bunch of skydivers to illustrate the point. That's a nice self-assembling system. Modular autonomous robotic assembly, maintenance, and servicing. Stupendous advances only in the last decade. Certainly a whole transformation since the 1970s allow you to envision a time in the very near-term future when quite complicated emergent behaviors will come from collections of cooperating robotic systems with relatively simple intelligence. Solar clippers, modular, reconfigurable, high-energy transports. We had a paper on that in our session yesterday on SPS. If you participated, you got to see it. If you didn't, too bad. And the idea of large phased array apertures, which we believe are becoming quite feasible now. So what about lunar solar power versus space solar power? What about the role of the moon? This is another 10-minute digression, which I won't go into, but I will just mention one thing, which is if you look at the energetics, the lowest energy way to provide energy to markets on the Earth, meaning how much energy do you have to invest to deliver the same amount of energy to the Earth? The lowest, so I'm not taking into account the infrastructure, the economics, none of that stuff. The lowest energy way to provide vast amounts of energy to the Earth is with lunar materials sent to GEO and used in GEO for solar power satellites. That is hands down the winner. It beats terrestrial power using terrestrial materials. It beats lunar solar using lunar materials. Turns out actually lunar surface power for lunar surface applications using ground solar materials from the Earth is not all that bad, but hands down the best thing to do if you're just looking energy to energy is make large-scale solar power systems on the moon, deploy them to Earth orbit so that they have a continuous sun and nice viewing angle on the targets on the ground. So in summary, interest continues and is in fact accelerated drastically in the last decade in new transformational approaches to global energy needs. Space solar power satellites can continue to be one of the only options that can provide the vast amounts of carbon neutral energy that will be needed during the coming decades. However, there are significant technology challenges. If somebody comes and tries to sell you 50,000 shares in SPS Inc., please don't buy unless it's me. It's at the sideline. But there are no fundamental issues. There are no fundamental issues in physics to resolve in making this thing happen. There are new concepts that have emerged during the last decade that make it much more feasible to think that economic viability will occur, not the least of which is that the price of energy has soared. In 1995, when we started the Fresh Look study, the price of oil was about $18 a barrel. Today it's at 74. That makes a huge difference. At the time, a notional rate of return on an investment was about 30%. Because of the dot-com bubble, you couldn't even talk about making an investment unless you were going to promise the 30% rate of return with oil at $18 a barrel. Well, today, 10 or 12% rates of return are regarded as quite excellent, and the price of oil is $74 a barrel. So there's financial concepts and advances, changes, evolution, as well as technical ones. All of these require no fundamental breakthroughs in physics, but they are hard, and they would truly transform how we pursue space activities. Thank you very much.
Thank you, John. Well, I noticed on one of those slides that John just had up there, it said that one of the challenges, technical challenges going forward is that exceptionally low-cost access to low Earth orbit for very large payloads is going to have to be developed. I don't know what the options for that might be other than the one that is being promoted and described and advocated for by our next speaker and panelist, Brad Edwards, and that is, of course, the space elevator. Brad Edwards is president and founder of Carbon Designs, developer of high-strength materials. Previously, he spent 11 years as a staff member at Los Alamos National Laboratory, leading space missions and development of advanced technology. The missions included an X-ray astronomy satellite named Alexis, and the design of missions for the Moon, Mars, and Europa. The technologies included cutting-edge X-ray detectors and the world's first optical cryocooler. But that was all in the past. Since leaving Los Alamos, Brad has led the development of the space elevator, originally under a NASA grant and now privately. During this effort, Edwards led a staff of 70 researchers at the Institute for Scientific Research and started several companies related to high-strength materials and space development. Edwards has written more than 50 technical articles in a broad range of areas, sits on the boards of several technical and private organizations, and has received multiple awards for his work, including the Sir Arthur Clarke Innovators Award in 2005. In 2002, I believe, he published what is literally the book on space elevators, and so he's the guy you want to listen to about this question, which I think is probably crucial to any possible success of a solar power satellite in space, and that is, how are we going to get these space elevators to work?
I think that meant solar sats. How are we going to get the solar sats to work? But, well, I'd like to thank John for covering the solar sat material, so I'll just sit back down. I was sort of blindsided by the change in topic on this panel. I realized it when I opened the program about 2 days ago, so my program's a bit more brief than John's. Can space save us in energy crisis? Well, I don't, as John pointed out in his, it's not a real simple question. It's not yes, and I sit back down. It's a big question that we don't know a lot of unknowns, don't know a lot of things on. Part of it's the timescales. What John has laid out is the discussion of solar power satellites, and they're big systems. You know, as he mentioned, they're millions of tons, and I don't know the exact number, but it depends on the designs. Tens of millions of tons or more, depending on how much of the planet you want to power. The question is, even with the best technology we can think of, even the one I'm going to show you here, how long is it going to take us to put those up and actually start addressing an energy crisis? If it takes us 30 years, depending on which stories you believe, then that's a few years too late. If we're talking about near term, I don't think John or I would say that we're going to have solar power satellites to power the U.S. in 5 years. If John wants to say that, I'll let him say that, but I'm not going to. And so, is it going to save us? It depends when that energy crisis is going to come. And I'm going to lay out a little bit on the timescales. But if it's in the next 15 years, I'm guessing space isn't going to help us too much. The options, one is, as John has pointed out, the solar power satellites, which I'll also talk a little bit about. Or another one that's brought up is helium-3, which you may be able to pull out of the regolith from the moon, or you may be able to pull out of the gas giants or something else, but it demands an infrastructure. Asteroids. Pull them out wherever. And but in any case, it requires a large infrastructure in space. John also had a similar plot here. These are from 3 different places. Actually, the middle one looks just like John's. And the lines on there are different scenarios, different discussions. This is basically production, gas, oil, natural fuels, fossil fuels. The line on the left, and again, this is up for debate, as John has said, but part of the reason we don't know, and part of the reason it's hard to answer the primary question of this panel, is there's so much politics and so much conflicting interests in answering, when's the energy crisis going to be and what's it going to be like, that we really don't know offhand. It could show up 5 years or it could show up in 100 years. If you look at these plots, again, these are from 3 different places. The line on the left, the vertical line on the left, indicates when half of the estimated reserves of fossil fuels have been used. Now, Again, we don't know. There's a lot of discrepancies in people quoting how many resources are there. But according to a couple of sources, they believe it's past. It happened a couple of years ago. The consumption is going up dramatically. If that one's not in debate, we'll all agree that consumption's going up here and abroad. China, India, various places that are developing are wanting more fuel, and we in the U.S., of course, use fuel like it's nothing.
Apparently, per capita consumption is already peaked and is going down.
Really? Well, that's nice. But what we're going to run into is, depending on who you talk to, a severe discrepancy in supply and demand could be anywhere from 5 years to, far off in the distant future. Question is, when's it going to happen? If it happens in 5 years, 10 years, can we respond fast enough to, avoid a real economic problem? Not that we completely run out of fuel, but if oil goes from $70 a gallon to up over $100 a gallon, which is predicted to do in a few months, to up over $500 a barrel in 5 or 10 years, how is that going to affect our economy? We're going to have severe economic issues. If it continues to go up and all of a sudden it takes us $20 a gallon to fill our car, food prices go up, everything goes up. And if it happens in 10 years, space is going to look like a luxury. People are going to worry about prices of food. They're going to worry about, their businesses. Inflation's going to be up. And I'm sorry, but I think, a lot of the space programs are going to be seen as strictly luxuries. They're going to have real problems with funding unless they can demonstrate how they're going to solve that economic problem, that energy problem. If it's out 50 years, well, we'll hang around and wait for the energy crisis to get critical, and then we'll run into that problem. We have a planning problem is what we've got. And sort of covering that, the good news is we've progressed to the point where we can solve pretty much all the issues we encounter. Or at least we believe we have, and we haven't run into some of the large ones. The bad news is that it's not a technology, it's the foresight. It's how long ahead of time are we willing to plan? When it gets real expensive for us to drive our cars, you're probably getting too late. So actually, I was recommending at one point that we all buy SUVs. And so the curve goes up dramatically. We hit that high price quickly while we still have lots of fuel reserves left. And then we all switch back to Yugos. And then we can survive a lot longer and start the planning stage to bring up the alternative energy. I'm guessing that's not going to happen. But this is another image that John also put up. This is Pat Rawlings' image, and it's one of the many designs. No matter what design you talk about, though, you're talking about many, many thousands of square meters, square kilometers of solar arrays, collectors, whichever version you're talking about. And if you only launch those without any structure involved for building, maintaining anything else, you're already talking about megatons into orbit, whichever one, LEO or GEO. That's a lot. Our shuttle launches 20 tons. To GEO, our largest rocket right now will launch 5 tons, roughly. There's talks about a high one. But if you're talking about millions of tons, that's many, many, many thousands of launches. Once a day, we're still talking many years just to launch them. That's after it's all built, ready to launch. So, how do we address that? John already pointed out a couple of these reports, and there's a couple of others, but I wasn't actually able to pull them up in the last day. Looking at the launches for this, and where it comes back to me is the cost of getting to orbit. There's discussions of putting these up in LEO, but I think the real optimal is putting them up in GEO. We can argue about that, but the cost you have to get down to is basically $800,000 a pound, a kilogram, depending on who you talk to. We talked to BP Solar directly, and their response was if you could get to $1,000 a kilogram to GEO, then they would put up the money to build the first solar power satellite, because then they could provide power to Southern California, of course a great market to supply to, at their current rates. And so from that format, if you get down to launch costs, which are a lot of the economic equation and which drives a lot of programs, technologically, if we can do it, great, but unless there's a return on investment, it often doesn't get done. So if you can get down to that level, then we're in good shape. Going to geo right now, that's sort of tough. If you're going to megatons and you're committed to that, you might be able to get a system that can do that. What we'd like to propose is, this is a space elevator that myself and a number of colleagues have been working on for a few years, and we've gone through a lot of the details, and there's been a number of talks and a couple of sessions on it. This system is essentially a ribbon going Earth to space. You can put mechanical climbers on it and ascend to space. LEO, GEO, throw it to the moon, Mars. No vibrations, no fairing, and very low operating costs, assuming that we build it. Now, where that helps is in a number of ways. The low cost to operation obviously is great. That fits within the $1,000 a kilogram, $1,000 a pound, whichever number you prefer. This would be able to do that. The operating costs are actually well below that. The low vibrations will allow you to launch less mass because the solar power satellites don't have to survive launch. Also, the no fairing, if you look at this, you could hang a full array as long as it can hang in 1G. You could hang it from a climber. You don't have to fold it up, stick it into a fairing. Again, it reduces complexity, it reduces some of the costs. You may even be able to just run it up to geo and leave it hanging on the ribbon itself. Again, it would reduce some of that. Also gives you access to the panels if you want to send people up, have them there. They can go up and down fairly inexpensively. Anyways, this may be able to reduce the costs to make something like solar power satellites economical. Part of the issue is the one that we've been talking about will launch 13 tons because that's the current space market. We can expand this up to something larger, 200 tons, but even at 200 tons, we're talking about, if you want, a million tons, we're still talking about many thousands of launches. So you need even something larger or more ribbons. So doing it is a challenge, but in the long term, solar power satellites are efficient, they are economical, and for a long-term future, because we're going to run out of nuclear, we're going to run out of coal, we're going to run out of oil, the question is when. At some point we have to switch to a completely renewable resource, and this is a viable one. If you want to get helium-3 from the moon or Mars, this would allow you to send the infrastructure up there to do that. Of course, somebody else has to design the fusion. We're going to have our hands full here. So I think the question of whether it can save us from an energy crisis really depends on how far ahead we're planning and what we want to put into it, what we want to expend to solve it. If we wait until we're paying $10 or $15 a gallon at the pump, my guess is we're going to be a little late. So, and we don't have to put all the megatons up at once, by the way. You start putting it up, you can start powering critical aspects, critical areas. But that's most of it, and so that gives you a baseline. If there's questions, and we got time, I think.
Yeah, I want to have a few questions here. And then probably open it up for a few questions from the crowd. But the first questions I have to kind of unite the two panelists here is, and for John first, is a space elevator a precondition to the building of a solar power satellite?
Why, yes. Good answer. What's that? Next question. No. The fundamental issue is how much does the deployed hardware cost wherever it is you're operating from?
Closer to the microphone.
Thank you. The fundamental question is, what does the deployed hardware cost? So if you're And you got to get somewhere in the ballpark of $2,000 to $5,000 a kilogram installed. That's it. If you're somewhere between $2,000 and $5,000 a kilogram, you have the potential to have economically competitive energy from space. And if your hardware costs $5,000, your transportation better be free. If your hardware is $1,000 a kilogram, which, by the way, jet aircraft are about $1,000 a kilogram, manufactured in lot sizes of thousands, very large objects manufactured by their thousands, then you can afford to spend $1,000, $2,000, or $3,000 per kilogram for Earth-to-orbit transportation, in space transportation, and so on. And it really comes down to how do you best deliver the deployed hardware at that cost point, that price point. And if you can do it, you got a shot. If you can't, if it's $20,000 a kilogram, forget about it.
So basically your answer is yes.
Well, some kind of low-cost launch approach is absolutely critical. Now, maybe it's low cost from the moon, but some kind of affordable, where affordable is radically cheaper than today, some kind of affordable space transportation systems are absolutely essential.
Brad, anything to add to that?
No, I think John very, very politely sort of dodged around committing to that one.
Thank you.
I noticed, John, on one of your slides that you had something that said that you didn't actually address directly. Nevertheless, as a topic, SPSS found no home at either NASA or DOE. Why not? And what does that say about where we are right now, about how these things are going to get developed, or whether they are, and who's going to do it, government, private industry, et cetera?
Well, fundamentally, there's no organization within the Department of Energy with responsibility for transformational ideas for energy, including space or wherever the ideas come from. And so there's no natural home. If it's DOE, it's not space. If it is space, it's not solar. DOE only works on solar for the ground. They do a little bit on energy for space in terms of RTGs, but they don't do anything for solar for space. So there's no natural bureaucratic home within the Department of Energy, and so they don't even know how to digest the idea. They don't have any vehicle, any mechanism, any machinery within the bureaucracy to talk about it. In NASA, there used to be. When NASA had as a policy objective the human exploration and development of space, when that was a policy objective for the space program, there was a natural intersection for being energy rich and talking about energy from space. And when that occurred, that was in the late 1990s, there was in fact a brief flicker, an opportunity when energy from space might have become part of the agenda. But as long as the purposes of NASA are aeronautics, earth science, space science, and exploration, in the sense of going and finding new things, there's no place, there's no policy purpose that allows you to say that NASA should spend taxpayer dollars on new kinds of space industries or energy from space. And so there's no home. In the bureaucracy, there is no home for this topic.
So how are we going to get those things up there?
If there's a tremendous need for some kind of governmental activity, because it's a long lead activity and a long lead issue, and there are significant questions of international cooperation, like spectrum allocation, that have to be worked through the International Telecommunications Union. You don't have some kind of government presence, that's really hard. But unless there's a change in policy to say, either to DOE or to NASA or to DARPA or to somebody, go do this. And this is, I don't know, energy independence or whatever it is, and you have a set of objectives, including SPS. I don't see it happening. Buzz would like to hammer on me a little, I think.
Yeah, I think actually, why don't we switch over to the audience, because I think we're probably running short on time. So I know that Buzz was already hammering on Brad a little bit this morning, talking about deceiving the youth of America about space elevators. So we'll give you a chance to raise a question for us up here, Buzz.
No, this doesn't have to do with If the present administration's vision is threatened by a new administration, would not a shift of policy so that vision for exploration does lead to energy, which is a problem today, would that not be a wise move for us to suggest to the administration that they expand the national policy so that it does include that, to preclude getting the legs cut out from underneath the vision for space exploration by the opposing administration?
I think it's a powerful formula. And I frankly, though, I wouldn't limit it to only energy from space, although this is an SBS session. I think that the formula before, which was exploration on one side of the coin, commercial development of space on the other side of the coin, that was a powerful formula. And we lost it a couple of years ago. If we got it back, it could only be good.
Well, commercial includes solar power satellites,
of course.
But it also includes a new industry of tourism into low Earth orbit.
Yeah, exactly.
Which really isn't authorized right now.
Right.
Brad, do you think there's any way that that government is going to develop these things? And do you think if not, then industry may step in and do it?
Actually, at the moment, we've been getting much more quicker response from private industry. There's actually a very good business case, for developing the elevator, which would lead to other commercial entities. What we're talking about is something that's a transportation, so it's not what you're doing at the other end, whether it's colonizing the moon, solar sats, whatever. It's sort of like the railroad, and that's received a lot more from private than from at least U.S. government.
Okay, can we take one or two more questions from the audience?
One more question.
David Livingston. There's David.
The guy with the mic.
For Brad or John or both of you, assuming you had an extremely cooperative public sector and private sector, and all of what you've been talking about is no longer an issue, what would be step 1, step 2, and step 3 of your Dream Wish implementation plan, and what would be the time frame of implementing those dream steps if we don't want to get caught until it's too late to do something?
From the solar power satellite side, we laid out a roadmap for the National Research Council. Step 1 is frankly to proceed, and you can do it in 3 to 5 years, depending on fairly modest funding, with a technology demonstrator, like the demonstrators that were done in the 60s and like ACTS, the COM demonstrator in the 80s, but done more efficiently, to demonstrate 100 to 200 kilowatt satellite power with power beaming. And then from there you sort of stepwise up, so that every 3 to 5 years you step up in terms of the level of performance, the advancement of technology, and you like punctuated evolution. You bring it to a demo every 3 to 5 years. If you did that, in 20 years, you'd transform space.
I think there are, as John pointed out, several technologies that are required for the solar power satellite, and you really have to focus on the key ones and start to develop those as quickly as possible. And so I would say right now I think we're getting to the point where we may be getting too late to start to hit an energy crisis. So we pretty much have to start immediately, and I think it probably has to be a very aggressive program. And you have to develop several of the components in parallel. You're going to have to be developing, the power beaming. You're going to have to be developing lightweight structures. Some of the operations in space. You're going to have to be developing a launch system, whether it's my system or another hit system. You have to be developing those, and you have to be moving on those as quickly as you can. We can't spend 15 years. Right now the Moon-Mars exploration. They're talking about testing things for the next 10 years, kind of thing, and building this or, working on that. And then it's like, in this case, we're going to be in a time crunch, and I think things need to move fairly quickly. And for that, it has to be, I think, a slightly different, operation scenario than what's currently being done. we need to get the major questions, major technologies, nailed down in the next, 5 years or some random number, so that we can start deploying in 10 to 15 years and hopefully start hitting the energy crisis, before it gets to us. And that would be very, very aggressive, but I think we sort of have to start doing that. Even if the first sets of solar power satellites we send up are not optimal or they're not the best design, start getting something up there that's going to help us. We need to extend the time frame between now and when the economy gets hurt enough that we can't afford to do it. Because once we get to that economy, then nobody's going to pay for it because they can't pay for it, and we start running into real issues. So we have to get something moving on it. And then maybe also just getting some of the other technologies going, the nuclear, getting nuclear or other alternative energies to extend that time frame.
John wanted to make one more quick comment.
One small plug. We're of course getting the hook, so we're going to get shuffled off, even though we started late. Nevertheless, I wanted to offer an invitation. If you were interested in the continuation of this discussion, there is a workshop scheduled on solar power satellites for tomorrow morning. It's in the program, and so we're going to continue this discussion for those who might care to be there between 9 and 11. Thank you.
Thanks to my panelists.
And then you